Alright, so the next topic we need to talk about is independence. And to motivate this, let's consider an example of two sort of just completely fictitious lotteries. Now, there are two different lotteries, and so let's look at two lotteries, and both pick four numbers from 0 to 9, and the order here does matter because you get different numbers. But the first one allows repeats of digits. And the second one does not. No repeats. Okay. And let's look at the following two events. First, let's look at the event that the last digit is even, and F, the event that the first three digits are even. And let's look at it in each of these cases. So for lottery 1, what is the probability that the first guy or the last digit is even? I mean, it seems pretty intuitive that it should be 1/2, but let's count it out exactly. What are the number of ways that the last digit could be even divided by the total number of outcomes? Well, there are 10 possible digits that could be chosen for each of the four times, so the number of outcomes is 10 to the 4. Now, the number of ways that the last digit can be even is 10 to the 3, which is the choices for the first three digits, times 5 for the 5 possibilities for the last digit. And when you cancel this out, you get 5/10, or you get 1/2. Great. Similarly, for Lotto 2, the probability of getting an even digit is also going to be 1/2. Actually, calculating this is a little bit difficult, but a little thought experiment should convince you of this. The probability of the last digit being even should be equal to the probability of the last digit being odd, because there are 5 even and 5 odd numbers to choose from. And these two are mutually exclusive events that add up to the whole sample space. The last digit is either even or odd, so this suggests that the probabilities should both be equal to 1/2, because they should add up to 1. So in any case, both of the probabilities here in both of the lotteries are 1/2. Now let's go back and look at Lotto 2. Lotto 1, and let's look at the probability that the last digit is even, given that the first three digits are even. So this will be the probability that the last digit is even and the first three digits are even, divided by the probability that the first three digits are even. Now, if all of the digits are even, that is 5 to the 4. There are 5 choices for each of the 4 different digits. Whereas in the bottom, what are the possibilities? Because we're allowing repeats. The first 3 digits have to be even, so there are 5 choices for each of those. But the last digit, if we're just assuming that the first 3 are even, the last one could be anything, so it's 5 to the thirds. 5 to the third times 10, and this simplifies to 1/2. That seems intuitive. It could be any, since it could be any number, half the time it's going to be even. But with Lotto 2, things are a bit different. The probability of E given F is the probability that the first 3 guys are even and the last guy is also even, divided by the probability that the first 3 guys are even. Now, if all of the numbers are even, there are 5 choices for the first digit, and then there are 4 choices for what the second digit can be, because I've already used an even number. third digit has 3 possibilities, and the fourth digit has 2. I can have any of the 5 even numbers for the first digit, any except for the first digit for the second, third, the third can be anything but the first 2, the fourth can be anything but the first 3. It's just really a permutation. While the number of ways that the first 3 digits can be even, and there are no restrictions on the last, well, there are 5 possible even digits for the first, 4 for the second because of no repeats, 3 for the third. But now once I get down to what can the last digit be, I'm not saying if the first 3 digits are odd that the last one has to be, if the first 3 digits are even, that the last one has to be even. It could be odd or even. We've used up 3 numbers, so there are 7 left. Now when I simplify this, this is equal to 2/7. So my point here is this. In Lotto 1, the probability of the last digit being even is the same as the probability of the last digit being even, given that the first 3 are even. And so we will say that E is independent of F. The probability that E happens does not depend upon whether F happens or not. Whereas Lotto 2, we had that the probability of E happening, which was 1/2, was not equal to the probability of the last digit being even, given that the first 3 were even. So here we will say that E is dependent on F. Whether E happens or not is, the probability of it happening is affected by whether F happens or not. Okay. So generally, our definition of independence is that E is independent of F if, this is a little bit different from how the book does it, but the main definition is that the probability of E, let me write it like this, the probability of E given F is equal to the probability of E. So whether E happens is not dependent upon whether F happens. Now I'd like to make a note, or a couple of notes. First of all, since the probability of E given F is equal to the probability of E and F divided by the probability of F, and we're assuming that this is equal to the probability of E when E is independent of F, if I'm to multiply, if I cross-multiply, I get that the probability of E times the probability of F is equal to the probability of E and F. So when E is independent of F, the product of the probabilities of E and F gives me the probability of E and F. This is kind of like the multiplication rule, which says that the number of ways that, I can make 2 choices is to multiply them together. This says the number of ways that, the probability of E and F happening is just the product. But that assumes independence. Second of all, continuing this note, if independence means that the probability of E times the probability of F is equal to the probability of E and F, then I can divide both sides by the probability of E, and what I end up with then is that the probability of F is equal to the probability of F given E. So that E is independent of F immediately implies that F is independent of E. Neither of the 2 guys has any effect on the other. So instead of saying that E is independent of F, we can say E and F are independent, or they are, you can say that they're independent. Yeah, pretty much it. They're independent events, whatever. Now we use the form of, first of all, let's check, let me just note that we use P of E times P of F equal to P of E intersect F most of the time. And we use this in a couple of different ways. The first way is so-called testing for independence. We consider two outcomes and we determine whether they are in fact independent of each other. So as a first example, let's say I flip a coin 2 times. Let's let E be that the first flip is heads, and F be that the first flip, that the second flip is also heads. Now the probability that the first is heads, well, you know, how many ways can that happen? It could be heads, heads, or heads, tails. And we know that the number of ways that you can flip a coin twice is 4. We've seen this many times. So it's 2 out of 4, it's 1/2. Similarly, and I'm not going to do the work, the probability that the second flip is heads is also 1/2. So now the question is the probability of E times the probability of F equal to the probability of E intersect with F. Because if so, then they're independent. If so, they're independent. Well, what is the probability of E intersect F? Well, E intersect F is that both flips are heads. So it's the number of things in this set divided by the number of things in our sample space, which is 1/4. So is 1/2 times 1/2 equal to 1/4? Yes. So E and F are independent. And what this really says is that 2 flips of a coin are independent. You can keep flipping a coin no matter what happens before. The next flip is going to be completely independent. It could be anything. The coin has no memory. The universe doesn't owe you anything. It could be nice to you, it could be mean to you, but just because you flipped a lot of tails doesn't mean the next one is going to be heads. On the other hand, let's consider something like this. Let's say you're dealt 2 cards from a 52 card deck. And let's let E be the event that the first card is an ace, and F be the event that the second card is an ace. Now the probability of the first or the second card being an ace is just the number of aces divided by the total number of cards. And there are 4 aces divided by 52 cards, which is 1/13. You know, that's pretty much it. You know, just here, just ignoring what I get on the second card, and here ignoring what I get on the first card, the chance that any card is an ace is 1/13. But what is the probability of E intersected with F? Well, why don't we just look at, why don't we use the product rule to do this, I suppose. Or let's sort of draw a tree diagram, sort of a couple of branches of a tree diagram. So I'm assuming that I get an ace from my first card and then an ace from my second card. There are all sorts of other things that can happen, but this is all we care about. The probability I get an ace from my first card is 4 out of 52, because there are 4 aces out of the 52 cards. But once I've been dealt an ace, there are only 3 left, and there are 51 cards left for that ace to come out of. So 4 out of 52, 3 out of 51, this is a conditional probability, assuming that I already got an ace. What do I do to figure out the actual probability? I take 452 times 351. This is the probability of an ace then an ace, which is the probability of E and F. Now, 4/52 is equal to 1/13, and 3/51 is equal to 1 over, I guess that's 17. And this is most certainly not equal to 1 over 13 times 1 over 13. So the probability of E and F is not equal to the probability of E times the probability of F, and this means that E and F are dependent. You might be excited that you get an ace for your first card, but that also means that you're less likely to be getting an ace for your second card. These are not independent events. Okay, now let's use independence. What do I mean by this? Well, we're going to make assumptions that, reasonable assumptions that, some events are independent of each other, and then we're going to use that to calculate probabilities. So, for example, we can assume that that rolls of a fair die are independent of each other. Maybe there's some sort of physics which says no, there's a slight, something that goes on, but generally no. You throw a die 2 times. What came up last time is not going to affect what came up this time. So let's look at a couple of things then. So A, what is the probability that I get a 1 twice in a row? Well, this is probability. Since we're assuming independence, this should be the probability of a 1 on the first roll times the probability of a 1 on the second roll. Now the probability of any digit coming up on any roll is 1 out of 6 because there's it's one digit out of 6 total digits. So it's 1/6 times 1/6, which is 1 out of 36. In fact, this corroborates the idea that if I roll, 2 dice, I get snake eyes, I get 2 1s 1/36 of the time. So that is the probability that I roll 2 1s in a row. Now something a little bit more complicated. What is the probability that I roll exactly 1 1 in 2 rolls? Well, let's break this up into 2 things. This is going to be the probability that I get a 1 and then not a 1, plus the probability that I get not a 1 and then a 1. Now, let me note that even, I was assuming that rolling a 1 is, let me just note this. If E and F are independent, so are E and F prime. So I said that rolling a 1 on 2 subsequent rolls, each roll of the 1 is independent of the other. Well, that also means that rolling a 1 is independent of not rolling a 1. So that means that the first probability here of rolling a 1, which is 1/6, and not rolling a 1, which is any of the other 5 digits times 6, that gives me the probability of rolling a 1 and then not a 1. The probability of rolling something that's not a 1 is 5/6 times the probability of rolling a 1, which is 1/6. So yay, whatever. So we get 5 over 36 plus 5 over 36, which is 10 over 36, which is 5 over 12. So I can actually expect to get a 1, exactly 1 1 in 2 rolls 5 out of, no, 36 divided by 2. Professor Bright, that's not equal to 12. That's equal to 18. So 5 out of 18. A little less than a third of the time you can expect to get exactly 1, 1, and 2 rolls. Interesting. Okay. Now we can also talk about independence of multiple events. And what this really means is that a bunch of events, E1, E2, all the way up to En, are independent if the knowledge, if the probability of any one event is independent, is unchanged, is the same as the conditional probability of that event given any combination of the rest of the events. So basically, no matter what happens over any of the other events, that's not going to affect what happens over one of the events. So an example I have here, and this is maybe only so realistic, but let's look at the Yankees Mets regular season games. That's an R. Regular season games. Now, the Yankees and the Mets play 6 times during the regular season, and historically, I guess at least since, I don't know, the mid-90s or something like that, in the late 90s, the Yankees, the probability that the Yankees win any given game is equal to 0.6. This is historical data. So now I can ask questions like, okay, 1, what is the probability that the Yankees, and let me take a step back, we can assume each outcome of each game, by which I mean a win or a loss, is independent of each other game. And I know that's not really necessarily true. You know, if the Yankees have beat the Mets 4 times out of 6, then the 5th game, maybe the Mets really want to win, and the Yankees might just be asleep, so whatever. Let's look at, say, the probability. What's the probability that the Yankees win all 6 games? Well, they have a 0.6 chance of winning the first game, and of winning the second game, of winning the third game, and the fourth game, and the 5th game, and the 6th game. The outcome of each of the games is independent, so I can just multiply the probability of them winning each of the 6 games together to get the probability they win all 6, and this is equal to approximately 0.047. A more difficult question would be, what's the probability that the Yankees win 5 games? Well, how many different combinations can they win 5 games? There are 6 ways they can win 5 games. Why? Because the number of ways they can win 5 games is 6C5. We're choosing 5 of the 6 games for them to win, and you can check that this is equal to 6. Okay. Now, any sequence is actually going to give the same probability. So the probability of a sequence, a specific sequence of 5 wins and 1 loss, will always have the same probability. We'll have 0.6 to the 5, which is the probability that they win 5 of the different games, times 0.4, which is the probability that they lose that one game. So that means that the probability that they win 5 games is 6 times the probability that they win those 5 games times the probability that they lose the one game that they lose. And this works out to about 0.187. And I'll let you think about this. But similarly, the probability that they win we already did 6 games. 4 games is going to be equal to 6C4, the number of ways of choosing 4 games for them to win, times 0.6 to the 4 times 0.4 squared. This is the probability of them winning the 4 games that they win, and this is the probability of them losing the 2 games that they lose, and altogether this is equal to 0.311. So a fourth question you can ask then is, what is the probability that the Yankees win the series? By which I mean they get they get a majority of the games. We'll just add up the previous numbers, and what you get is a 0.31. No, that's the wrong number. 0.545. So they are almost guaranteed to win a majority of the games. Well, not almost guaranteed, but more than half the time they should win almost all the games. But even though they do win 60% of the games, only 55% of the time do you expect them to win a majority of the games. Great.